Hello friends, we meet after a long time, and today we are going to study a very important topic in quantum physics, which is particle in a 1D box. And this will give us important concepts about quantum confinement, degeneracy, discrete energy states, and so on. The first step in this regard is to define the potential. And if we look at this potential, we see that this is a 1D box with perfectly rigid walls or an infinite square potential of length A, and the particle of mass m is confined within this box. So the walls of this 1D potential, they are extending up to infinity. There is no way the particle can escape out of this, but inside the box, the particle is free. The time-independent Schrödinger equation can be written as d squared psi dx squared plus twice m by h cut squared e minus v psi equals to 0. In this region, the potential is 0, so we can simplify this and we write as d squared psi dx squared plus k squared psi equals to 0, where k squared is twice m e by h cut squared. General solution of the equation number 2 is a sine kx plus b cosine kx. We take the sine and cosine form because it will be useful in our solution in this case. And the constants a and b are to be determined from the boundary conditions. So what are the boundary conditions? Since the potential is infinity at the walls, psi will vanish. And that means at x equals to 0 and a, psi should be equals to 0. Putting the first boundary condition, we can easily get the coefficient b to be 0. That leaves us with this expression. And now we put the second boundary condition. We see that psi a equals to 0, and that implies a sine k equals to 0. A equals to 0 will not be an acceptable result because in that case, the wave function will become 0 for all values of x. So everywhere it will become 0. And that is not possible because the particle is very much within the box. It is indeed there. Thus, we have to take this result, sine k should be 0. This means k should be an integral multiple of pi by a, where n is an integer. This n pi by a, we can write k as this. N also cannot be 0 as the wave function cannot vanish inside the box. So the same logic from this case will apply here as well. And we see that with confinement, k is no longer continuous, but now it has become discrete. Only certain values of k are allowed. Thus, the solution to the time-independent Schrödinger equation, which satisfies our boundary condition, can be written as this: psi n x is a sine n pi x by a. Now we will normalize the wave function. For that, we can take n equals to 1 and set the integration limits 0 to a. Because we know the particle is definitely confined within the box, it cannot go outside. That's why from minus infinity to plus infinity, we can just set these integral limits from 0 to a. And that gives us the value of a to be square root upon 2 by a. So the normalized wave function or eigenfunction for this problem should be of this form: psi nx is square root upon 2 by a sine n pi x by a, where n is an integer 1, 2, 3, and such. And since we know k is n pi by a, we use that and equate with the previous relation in 3. And we find the energy eigenvalues, which gives us the energy for the nth state, En, is n squared pi squared h cut squared by twice ma squared. So here is a key concept of energy quantization, that the energy is no longer continuous like for a free particle, but it has now become discrete. This energy is known as the ground state energy. If we put n equals to 1, this is what we get. It is also known as the 0 point energy. N equals to 2 is the first excited state, n equals to 3 is the second excited state, and so on. As this discretization of energy states is happening due to quantum confinement of a system, the system is being confined and then it is getting quantized, the energy is getting quantized. So that is the key concept behind quantum confinement. And the name also comes from this, that quantization due to confinement is happening in this case. So we call it quantum confinement. If we have a stronger confinement, that is a smaller length of the box, this length squared is inversely proportional to the energy. So that would mean not just an increase in energy, but if we closely look at it, more separated energy states. If we make the box smaller, it will be more separated, the energies will be more sparsely spaced, and all the energies will also rise at the same time. Moreover, this mass should be small enough for these differences in energies to be observable. If we can sketch the energy levels, wave functions, and probability density, we will see the wave functions for the ground state, first excited state, second excited state, and so on. They are alternating functions of even and odd parity. So the ground state has even parity, the first excited state will have odd parity, and so on. The wavelength of the different quantum states is given by this quantity lambda. So the de Broglie wavelength will look like this. The number of nodes will be n minus 1. That is why the ground state has no nodes, because in this case n equals to 1. First excited state has only one node, second excited state has two nodes, because here n equals to 3. And there are antinodes like this, which are the maxima, or rather the extrema in this case. So they are equal to n, and those we can see this for the ground state, there is one antinode. For first excited state, n equals to 2, so there are two antinodes, and likewise. If the probability densities are sketched, they look like this, because it is a mod psi n squared, which is psi star psi. It is always a positive quantity. And these diagrams, these sketches are not to scale, but we get an idea about how this system is going to look. If we extend this confinement to 3D, we will get a very exciting idea of degeneracy. Like we had for confinement in only x direction, we had a n square. We will see that if we introduce confinement in other directions as well, we'll get n squared for z direction as well. So we determine this by n2 square. We can label the confinement in the z direction with n3 square, and like that. These N1, N2, N3, they are all representing a quantum number, and different N means a different quantum state. Hence, an energy level can have different quantum states for the same energy. Like in this case, n squared is 6 in all the three cases, but the energy states, the quantum numbers are different, like 112, 121, 211. And also in few other cases, we can see this happening. This is called threefold degeneracy because there are three different quantum states having the same energy. Here also we see threefold degeneracy. And some states may not be degenerate. Thus, the concept of degeneracy can also be understood very elegantly from the particle in a box problem. Now we come to the time dependence of the whole problem. We had solved the Schrödinger equation in the time independent form and found psi x. To get the time dependent form, we can just multiply with exponential minus iet by h cut. And this is what the final form with the time dependence included look like. The states we had sketched previously, if you see, they are fixed in time, they're not moving around. But here, due to the incorporation of the time factor, the states have become oscillatory in nature. So they're oscillating around. And also the e to the power I theta kind of factor that introduces an imaginary part. So there is a real part and imaginary part shown in blue and red. And the particle is moving at constant velocity in the classical picture back and forth between the walls. That is the classical picture of such a system. And this is the quantum picture of such a system, the dynamic quantum picture of such a system. This is the ground state, the first excited state, the second excited state, and so on. In real world, the examples of quantum confinement can be seen in low dimensional materials. If we confine one dimension, like in this case, so the electrons in the system are free to move in the other two dimensions, that becomes a 2D material. If both the directions are confined, then it becomes a 1D material like a nanotube or a nanowire. If all the three directions are confined, then it becomes a quantum dot. Like this, there are discrete energy states, and there is a gap that is increasing with reducing particle size. Quantum world devices are also employed in many cases, and so are charge trap devices. And these are some real world examples of a system like particle in a box. Here, these two systems, they are not exactly infinite boxes, but still somewhat they are resembling our case. So more about these systems we can discuss in the next upcoming video lectures. And these are the books I would suggest you to read. Please follow my YouTube channel. You can like, share, and subscribe. We will again try to keep uploading videos quite regularly. There is a QR code for my website as well. And this is a book I have authored, which has some introductory chapters on quantum physics, nanomaterials, and such interesting topics. So, with that, I come to the end of this video lecture today, and I'll see you again in our next upload. Thank you. Bye bye.